Let's begin today's class with a quick review about what we've covered so far with capacitors. This will be our second and last online class on capacitors, and then we'll be moving on to the next chapter. I will mention, though, that we're going to learn much more about how capacitors actually act in a circuit, but we can't do that until we know a little bit more about current and resistors, which we'll be learning about in the next few chapters. To review what we've talked about with capacitors, we know that capacitors are fundamentally made up of two conductors separated by a small distance. And the easiest type of capacitor to visualize is just one that is made up of two parallel plates, as shown in this diagram. When we connect a capacitor to a voltage source or electric potential difference, like a battery, what we find is that the capacitor will charge up, and one plate will become positively charged, the other plate will become negatively charged. The capacitance of a capacitor is simply telling you how much charge the capacitor can store for a given voltage. So in other words, a higher capacitance rating simply means that for a given voltage V, you will store more charge. So higher capacitance capacitors store more charge per voltage. The unit for capacitance is the farad, and as I mentioned in our last online class, that's a big amount of capacitance. So most of the capacitors you'll actually see in a circuit range in the picofarad to microfarad range. Okay, that's usually what you're going to see in most electronics. Before we get more into the details of capacitors, I want to talk about just series and parallel circuits in general. So first of all, in this slide, a circle with an X in it, that just represents any circuit component. So in other words, that could be a resistor, it could be a light bulb, it could be a capacitor, anything that I can connect in the circuit. So these are general rules that are always true for series and parallel circuits. The other thing that I want to do before I talk about that is just introduce briefly to you the idea of current. This is something that we'll be talking much more about in a later chapter. But what a current in a circuit represents is it represents a flow of electric charges around the circuit. The way that current is defined is that current is equal to the amount of charge that goes by a point in the circuit per time. So let's say there was a circuit, or let's say there was a current flowing around in that circuit. If I just watched one point in this wire and added up the amount of charge that passes by in a certain amount of time, that would be the current in the circuit. You can see that the unit for current is going to be a coulomb per second, and because current is an important quantity, we give that its own unit, which is the ampere. And oftentimes we just say amps, but it's really the ampere. Okay, so let's look at what we mean by a parallel or a series circuit. In a parallel circuit, everything is connected in such a way that it's really connected directly to the battery. You'll notice that the current can get to item 1, item 2, or item 3 without going through the other circuit elements. In this case, whatever the voltage is that the battery is providing is going to then also be the voltage or electric potential difference across each of our circuit elements. So we find that for a parallel circuit, the voltage provided by the battery is equal to the voltage across each of the elements that make up the circuit. Now, current, on the other hand, is not going to be the same everywhere. If we think about the current coming out of the battery, you'll notice that when it gets to here, to that junction, it has two choices. And when it gets to this junction, it has another two choices. So if we look at the current going through our first circuit element, and the current going through our second, and the current going through our third, we can see that the total current that leaves the battery is going to be equal to the sum of the currents that flow through the three circuit elements. Okay, so that's a parallel circuit. Now, one of the interesting things about a parallel circuit, picture these three things as being light bulbs. If you unscrew one of those light bulbs or one of them burns out, it does not affect the other two because they're all essentially independently connected to the battery. Okay, let's talk about series circuits. In a series circuit, the current that leaves the battery is going to be the same as the current everywhere because you'll notice the current has nowhere to go. Once it's coming along here, it has no choice but to go through our first circuit element or our second or our third to get back to the battery. So in a series circuit, you'll notice we get the opposite rules. In other words, the current that leaves the battery is the same as the current everywhere else in the circuit. And that's an important thing, that the current is the same everywhere in a series circuit. Also, the way the voltage works is now the voltage adds. The voltage put out by the battery, or the electric potential difference, is equal to the sum of the electric potential difference across each of our three circuit elements. Okay, so I want you to just notice that the rules are reversed between parallel and series. And again, this is true whether we're talking about resistors, light bulbs, capacitors, etc. Notice, by the way, in a series circuit, if you unplug that element, then all of the elements go dark. In other words, if that's a light bulb and it burns out or you unplug it, no current can flow in the circuit because it can't flow through that element anymore. And so that's kind of one of the hallmarks of a series circuit, that if one of the items burns out, they all burn out. All right, so we want to look at how capacitors connected in parallel add up. In other words, what we want to figure out is if I've got this circuit where I've got three capacitors, notice they are connected in parallel, meaning that the voltage across all of them is the same. We want to know what one capacitor could I replace those three capacitors with and have the same behavior. So what we're looking for is what is the equivalent capacitance, and we'll call that CEQ. All right, well, in order to figure this out, we're going to use the rules that we just talked about for parallel circuits. The one difference is that when we're talking about capacitors, instead of talking about current, we're going to talk about charge. Remember, though, that current and charge are directly related to each other. So the rules that I talked about on the last slide for current also apply to charges. Well, in a parallel circuit then, we know that the charge on this equivalent capacitor is going to be equal to the sum of the charges in our original circuit. We also know that for anything in parallel, the voltage across each of our capacitors is going to be equal to the voltage that the battery is putting out. And so what we're going to do now is we're going to take this formula, as well as using this one, and come up with a rule for how capacitors add in parallel. The one thing we have to remember is that by definition, C is Q over V. And so what I'm going to do is I'm going to replace Q with C equivalent times V. In other words, the charge Q on my equivalent capacitor is just C equivalent times V based on our definition of capacitance. So that's got to be equal to C1 V1 plus C2 V2 plus C3 V3. In other words, I'm just plugging in the fact that the voltage across capacitor 1 is V1. That's got to, those multiplied together is equal to Q1. But now I'm going to use this fact and see that I can replace all of those V's, or more correctly, I can just cancel them out because we know that all the V's are the same. And so I get rid of those, and what I end up with is that the equivalent capacitance is equal to the sum of those three individual capacitors. And obviously you can generalize this to any number of capacitors in parallel. Okay, so if I've got three capacitors in parallel and I want to replace them with one, I now know how to do it. Let's look at what happens with capacitors in series. The first thing is, in a series circuit, we know the current is the same everywhere. So that means that the charge has to be the same everywhere. And therefore, the one capacitor that I can replace those three with has to have a charge on it equal to the charge on each of those individual capacitors. So Q is going to be equal to Q1 and is going to be equal to Q2, which is equal to Q3. Now, in the diagram here, it just shows them all as being equal already. One of the things to think about here is that charge never flows through a capacitor. So in other words, when you connect this circuit and a current starts flowing, as this plate charges, notice none of the charges in this part of the circuit can ever get in here because capacitors are essentially a break in the wire. But what happens is, as this plate becomes positive, then this plate will become negative, which makes this plate positive, which makes this plate negative. And so if you think about it, really in each section of the circuit, in section A and section B, no charge ever leaves those two sections, but it gets redistributed. Okay, we also know that for capacitors connected in series, that the voltage is going to be equal to the sum of the voltage across each one. So again, that's our other rule for how things connect in series. And what we're now going to do is just take this formula and rewrite it. Again, I'm using the fact that C is equal to Q over V. So notice that means V is equal to Q over C. And so I'm going to replace V, the voltage of the battery, with C equivalent and Q. So in other words, V is Q, the total charge, over C equivalent. V1 would be Q1 over C1. V2 would be Q2 over C2. And V3 would be Q3 over C3. Okay, so now you'll notice that again, using this idea that all of the charges are the same, I can divide through by Q, and I get that 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And that's how capacitors add in series. Okay, so what kind of problems can we do with this information? Well, here is a typical kind of problem that you'll be asked to do on homework and exams and such. And the question says, what is the equivalent capacitance of this circuit? And then if the battery voltage is 10 volts, what is the charge and the voltage on each capacitor? By the way, this is the harder part of the problem. The equivalent capacitance is just applying the two formulas that we just derived. The second part, though, you really have to think about what's going on. Okay, so first of all, when we say that capacitors are in series, it's important to understand that what we mean is that the current has no choice, right? If we go into the first capacitor, there's no other way to go except to go through the second capacitor, okay? So that's what series means. For parallel, what we mean is that the circuit splits, goes through the two objects independently, and then comes back together. Okay, so if two objects like these two capacitors are in parallel, the circuit has to split, go to them, and then come back together. You'll notice if we look at the circuit in the problem, the first thing we need to understand is that these two capacitors are connected in series, because once we go down this path, we have to go through the other capacitor to get out. So they're definitely in series. And so that's the pair that we want to start with. The first thing we want to do is figure out what is the equivalent capacitance of these two. Well, from the formula we have, we know that they add as the inverse. So 1 over C23 is equal to 1 over C2 plus 1 over C3. Let me show you the notation that I'm going to be using and that I want you to use. Basically, when you combine capacitors in some way, denote the new capacitor with both numbers that went into it, okay? So that way I'll know what you're talking about. Just to show you the math here, 1 over C23 is equal to 1 over 15 plus 1 over 22. Notice, by the way, I'm not converting out of microfarads because that'll just keep my answer in microfarads. I want you to pause the video and calculate the answer for C23. Okay, so hopefully that you got that C23 is equal to 8.92 microfarads. If you didn't get that, my guess is that you added the two fractions, but you forgot to then do 1 over to find C23. That is the most common mistake that students make on problems involving capacitors. When you're adding capacitors in series, it's really easy to do this part, this side, but notice that's not C23, that's 1 over C23. Okay, so make sure that you remember that. Okay, so what I want to encourage you to do, and when I say encourage, I mean I'm going to require you to do it on an exam, is every time you combine capacitors, I want you to redraw the circuit so you know what you now have. In other words, we've still got our battery down here, but now instead of 2 capacitors here, we only have 1, and we're calling that C23. We still have capacitor 1 up here. And remember that ultimately what we're trying to do is combining both of those to get just one capacitor. So you'll notice that if we can now combine C1 and C23, we can get to where we want to get to, which is just one equivalent capacitance, which I'm always going to call CEQ. Okay, so to do that, you'll notice that C1 and C23, they are now in parallel because again, the current would come up, it splits, it has to go, or it can go either way between them, and then it comes back together. So C equivalent is going to be C1 plus C23, and that's going to be 18.9 microfarads. Okay, so we've now done the easy part of the problem, which is finding the equivalent capacitance. But how do we figure out the voltage and the charge on each of the original capacitors? This is where it's really helpful to have drawn these diagrams as you go along. Because what I want to think about is I now know everything there is to know essentially about this circuit. I know C equivalent is 18.9 microfarads. I know the voltage of this battery is 10 volts. And I can now work my way backwards through the circuits. So always work your way backwards when trying to answer the questions. Okay, so first of all, you'll notice that right away, if I look at this circuit, the original circuit, I know the voltage across C1 because notice C1 is directly connected to the battery. Another way to say that is it is in parallel with the battery. So I know that V1 is 10 volts. So that's one of the things that I'm trying to find. Well, if I know the voltage across a capacitor, then I can easily calculate its charge. In other words, the charge on C1 is just going to be C1 times V1. And that is equal to 100 microcoulombs. By the way, notice the trick that I'm using that I talked about last time. If your charge is in microcoulombs and you're using volts, then your capacitance will be in microfarads and vice versa. So I don't have to convert out of microfarads. I just need to know that when I calculate my charge, it's going to be in microcoulombs. Okay, so that makes these problems a little bit less cumbersome. Okay, so I've got the charge on capacitor 1. The next thing I want to do is I want to start working on C23. Notice that for C23, I also know the voltage because C23 is directly in parallel with the battery. So V23 is also 10 volts. Well, that means that Q23 is going to be equal to V23 times C23. And if you calculate that, you should find that you get 89 microcoulombs. Okay, so I'm just taking what we had for C23 and multiplying it by 10 volts. Okay, so now the question is, we know about this capacitor. What does that tell us about these two capacitors? This is where you need to remember that when you have capacitors in series, the charge on each of them is the same and is the same as the one capacitor you replace them with. So based on this, Q2 and Q3 have to have a charge of 89 microcoulombs. So that is the key piece of information that, again, sometimes students forget. That's why I started by talking about series and parallel. You have to remember that in series, the charge on each capacitor is the same and is the same as on the replacement capacitor. Okay, so once I've got the charge on each of those, the last thing we have to do is find the voltage on each of these capacitors. And I can do that pretty easily. I know V2 is going to be equal to Q2 over C2. By the way, notice that we're just using C equals Q over V all the time, right? So that's kind of the fundamental definition of capacitance that we're just using throughout these problems. Okay, so V2 is Q2 over C2. If you work that out, you should get 5.9 volts. And if you work out V3, which would be Q3 over C3, what you get is 4.1 volts. Okay, and those are our last two results that we needed. So you'll notice that in this problem, we found the equivalent capacitance, and then we worked our way back through the circuit to find the charge on each of the original capacitors and the voltage across them. I want you to also notice that we know this voltage is 10 volts. Notice that the voltage from here to here also has to be 10 volts. And notice that these correctly add to 10 volts. Okay. Another check that we have is we can also look at the total charge. If we wanted to do that, the total charge on our equivalent capacitance, you'll notice that since Q is equal to CV, that we can see our total charge would be 10 times 18.9, 189 microcoulombs. And you'll notice that if we add up the charge here and the charge here, we also get 189. Okay, let's have you do a problem on your own. So I'd like you to pause the video and see how far you can get going through this problem. Okay, so let's see how you did. So, excuse me, in this problem, hopefully the first thing you realize is that you've got to combine these two capacitors first because they're in parallel. And so the first step is going to be to replace those two with one capacitor. Here's C1, and we're going to replace C2 and C3 with one capacitor, which we're going to call C23. So this would be the first of your equivalent circuits. Now, in order to do that, we know that when capacitors are in parallel, their capacitances just add. So C23 is just C2 plus C3. And when we do that, we get 25 microfarads. Okay, now we want to combine C1 and C23. You'll notice that since they are in series, we're going to have to add those the way capacitors add in series. So C equivalent is going to be 1 over C equivalent is equal to 1 over C1 plus 1 over C23. Now again, make sure that you're actually trying to do this on your own and doing the calculations so that you discover whether you're doing it right or not, because it's so easy to forget to take 1 over the right-hand side there to get the final CEQ. So if you haven't done it yet, if you didn't do it already, do it before you continue on. All right, hopefully what you got was C equivalent is equal to 4.17 microfarads. Okay, so we found the equivalent capacitance. Again, that's the easy part of the problem. The more difficult part of these problems is finding the voltage and the charge on each of our original capacitors. You'll notice that in this problem, I do not know the voltage across any of the capacitors to start out because none of the capacitors are directly in parallel with the battery. So again, I want to work my way back through my circuits. I know that my voltage is 12 volts, and I know that, and we figured out the equivalent capacitance. So notice that I can find the charge on my equivalent capacitor. In other words, the total charge on C equivalent is just C equivalent times V. And we've got 4.17 times 12 volts. And that gives us a charge of 50 microcoulombs. Okay, so that's Q, the charge on our equivalent capacitor. Now, again, you're dead in the water here unless you remember how charges work for capacitors in series. What we've said is that the charge on each of these capacitors is the same and will be the same as on the one charge that replaces them. So notice that once you've found the charge on C equivalent, that is the charge on both C1 and C23. Okay. Now, once we know the charge on C1, we can find the voltage on C1. So we know that the voltage is just going to be equal to the charge over the capacitance. And again, we're just always rearranging C is equal to Q over V, right? That's how I'm coming up with these different equations. So, excuse me, we get 50 microcoulombs divided by 5 microfarads. And notice that if we have microcoulombs divided by microfarads, that just gives us volts. And so we find the voltage across capacitor 1 is 10 volts. So if this is 12 and this is 10, then what's the voltage have to be from here to here? Well, hopefully you understand that since the voltages add as we come around, and probably it's maybe easier to see in this circuit. In other words, if this voltage is 12, and we've now figured out that this voltage is 10, then this voltage has to be 2. So that's how we know the voltage across C23. If the voltage across C23 is 2 volts, well then that's also the voltage across C2, and that's also the voltage across C3, again because of our basic rules of how parallel circuits work. So we've now found that the voltage across capacitor 2 and the voltage across capacitor 3 are equal to 2 volts. And then finally, the last thing we have to do is find the charge on each of those. The charge on C2 is just going to be C2 times V2, and that comes out to 20 microcoulombs. The charge on capacitor 3 is C3 times V3, and that comes out to be 30 microcoulombs. So those are our last answers that we needed to find. Now, I want to look at how we can check things in this problem. Notice that we know the charge on C1 and C23 are both 50 microcoulombs. Well, one of the things that we learned about with parallel circuits is the charge on this plus the charge on this should equal the charge on the equivalent capacitor. And you'll notice that we find that is true. Notice that these two add to 50 microcoulombs. So you can always do these kind of checks when you're doing these problems, which is good because you have a sense that you actually got the problem right. Okay, so hopefully you've got some understanding now of how capacitors add in series and parallel, and how we can determine the charge and the voltage on each capacitor in a complicated circuit like this. The last thing that I want to talk about is just really kind of a conceptual idea, which is I just want to show you that with our knowledge about capacitors, we can actually figure out how much energy is stored in an electric field. Now, obviously, we know electric fields can have energy or carry energy, because if you think about the fact that all of our energy essentially comes from the sun, and that's coming in the form of electromagnetic waves, well, the electric and magnetic fields have to be carrying the energy. And to figure this out, or to see this from the point of view of a capacitor, I want to use, first of all, just how much energy is stored in a capacitor. Remember, we derived that formula earlier. Remember, this is the capacitance of a parallel plate capacitor, and this is the relationship between the electric field in a capacitor and the voltage across the capacitor and the separation. By the way, when we've seen this earlier in a previous chapter, we wrote it as delta V is equal to E times delta R. Okay? But again, remember what V represents now is what delta V used to represent, which is electric potential difference. Okay, so if I look at the energy stored in a capacitor, and I want to look at it instead of in terms of voltage, but in terms of the electric field, I can do that. I'm going to replace C with epsilon naught A over D, and I'm going to replace V with E times D. So that's going to be E squared D squared since the V was squared. And when I look at this, you'll notice that I can cancel the D with the squared, and I get 1/2 epsilon naught E squared A D. Okay? But now I want to think about what is this? What is A times D? If you can picture these two parallel plates separated by a distance D, so this distance is D, and each of the plates has an area A, you'll notice that what A times D is it is the volume contained in the capacitor. And so what we do is we say, since AD is equal to the volume, we can define the energy density of an electric field. And we do that by simply taking the energy and dividing by the volume. So remember, density in general, any kind of density is something per volume, right? You think of regular density, it's mass per volume. So we use a small u to represent energy density. And what we get is 1/2 epsilon naught E squared. So that is an important result if you're trying to figure out how much energy there is per volume anytime there's an electric field in a region of space. If you know the strength of the electric field, you can calculate how much energy is stored in that electric field. And we're going to come back to this result in a later chapter. So don't worry about this too much right now, but just know that electric fields can have energy.